Okay, so let us continue and let me close this. Hold on a second. Let me share my screen with you again. Okay. Let's close this and open up a new page. So all right, so before we actually discretize this problem and solve it with the so-called lumped parameter approximation, let's attempt to at least see or feel how the early pass method works. Okay, so try early pass. Early pass method, not in the sense of designing a controller, but just trying to solve the differential equation. Okay, early pass method with some approximations. Before discussing the so-called lumped parameter approximation.
Hocam kaydı başlattık mı acaba?
Başlattık, evet. Bir saniye gene bir kontrol edelim. Evet. Parameter approximation. Okay, so we will make a number of assumptions. First of all, we will try to solve the partial differential equation around the steady state solution. Okay, steady state solution. So that we basically have an initial condition that's going to be equal to 0. Okay, so let's say that our steady state solution is TE, okay, which is the temperature of the environment. Okay, the ambient temperature. So we assume that we let the system settle in the ambient temperature. So what's going to happen is that we are at steady state, we are at a non-zero temperature, but what we will see is that we will apply a certain step function at one of the boundaries, and we will see what's happening around the steady state in response to that excitation. Okay? So basically, what's going to be, this will lead us to obtain essentially a delta variable solution. Let's call this tau instead of t. So tau xt will be simply txt minus te. Okay, so we will be looking at what's happening with respect to time in response to an excitation around the steady state value. Okay, so we will also assume that we have an infinite slab of material. That means we will assume that we have this insulator, right? But this thing actually goes on, and you have one boundary over here at x is equal to 0, but then you have no other boundary. It's just going to x is equal to 0. Okay? This will allow us to specify only one boundary condition. And we will. This is going to simplify certain things, as we will see in a minute. Having an infinite slab, the other end being at infinity. Okay, so let's our partial differential equation. Let's remember that was equal to del tau xt over del t. That was equal to a constant, times del square tau xt over del x squared. Okay. Now what we will do is we will again use the Laplace transform, but Laplace transform is taken with respect to the time variable. Okay. So what we will have is s times tau. The x variable still stays, but the time variable is transformed into the frequency variable, minus the initial condition, which is the temperature, again at the same x, but at the 0 time. Okay, so this is our initial condition. Initial condition, still a function of x. Okay, that is equal to a times, we still have the partial differential equation, partial difference or partial derivative here, second order partial derivative, because it is with respect to the space variable. Now what's the end result of this is that note the partial differential equation is reduced into an ordinary differential equation, or let me also short into an ODE in X. Okay, so by using the Laplace transform, remember for ordinary differential equations where you have only the time variable, the Laplace transform is huge, because when you take the Laplace transform, you eliminate the differential equation and you return into an algebraic equation, so that things become so much easier to solve. Okay, here because we have a partial differential equation of two variables, taking the Laplace transform with respect to the time variable actually eliminates one of the variables, or eliminates the derivative with respect to one of the variables, but the other derivative remains, so you end up with an ordinary differential equation. Okay?
Order nasıl artık? Zaten öncesinde de 2 değil miydi orderımız? Hani parçalda da sonuçta x'in ikinci türevinde.
Order'la ilgili hiçbir şey söylemedim. Söylediğim şey şuydu.
Öyle bir şey yazmıştım.
Nereye yazdım?
Bu early yaptığımız zaman
Şeyi hatırlarsanız early pass metodunda order'ın değişimiyle ilgili hiçbir şey söylemedik. Pardon, bir saniye. Şöyle bir hata yaptık burada. Değil mi? Teşekkür ederim. Şimdi tamam mı? Tamam. Başka soru var mı? Dediğiniz gibi early pass metodunda sonuçta şey var. Finite element kullanıyoruz. Burada şu anda onu yapmıyoruz. Late pass metoduna bakıyoruz. Yani partial differential equation'ı doğrudan çözmeye çalışıyoruz şu anda. Soru var mı? Okay.
Hocam ben de bir şey merak ediyordum da.
Buyurun.
Neden sadece sol tarafın noktasını alıyoruz da sağ tarafınkini almıyoruz? Orada T'ye bağlı bir şey kalmıyor.
Ona da teşekkür ediyorum. Orada da bir ufak hatamız var. Şöyle ki dediğiniz gibi iki tarafın birden Laplace transformunu alıyoruz. Dolayısıyla orada derivatif duruyor ama aynen dediğiniz gibi şurası s variable olmak zorunda. Doğru mu?
Aynen.
Tamam. Teşekkür ederim. Başka soru var mı? Güzel. Let's further assume that we have zero initial condition, tau x0 equals to 0. This comes naturally because we assumed the system to be at equilibrium at the steady state, and we work with the delta variable. So although the actual temperature is not 0, the delta variable is equal to 0 because we are looking at starting from the steady state. Okay? Because we have T x0 is equal to TE. Okay? Because we start with the equilibrium. And that's the end of the infinite slab is not affected by transient phenomena. What does that mean? That means because of the infinite slab assumption, the other end is so far away that anything transient happening at one of the boundaries will have no effect on the other end at infinity. Okay, so basically we will have T xt will be equal to 0 as x goes to infinity. Okay. That means nothing's going to happen at the infinite end at the delta variable. So if initially the other end at infinity is at the the steady state temperature, it's going to always stay at the steady state temperature, and therefore the delta variable will not change from 0. It starts from 0, but it's not going to have anything happening as time goes on. Okay? Is there any questions related with these? So what's going to happen is that we will apply a transient input. We will apply, for example, a step input at the left-hand boundary. Nothing's going to happen at the infinite other end, but something's going to happen throughout the material as we have the x variable. Okay, and temperature will change with respect to time for every chosen x variable, as we will see. Okay, so we have basically from that, because the initial condition also is gone, del square tau xs over del x square is now equal to, I'm going to basically write it this way, s over a square root and square. Okay, so that cancels the square root, but you will see why I'm writing it this way, because it makes it kind of easier to see why the solution is as is. Okay, so tau xs over here. So the homogeneous solution to this equation is given by, maybe you might remember this kind of trials or this kind of proposals for a solution from your differential equations courses. So tau xs has a proposed solution of a constant to e to the power minus x s over a square root plus k2 e to the power x s over a square root. Now it's not very easy to propose this solution, but it's very easy to verify that it's a solution. If you put this in the differential equation, you will see that it's going to satisfy the differential equation. Okay? So this can be shown to be a solution by putting it inside the differential equation. Okay. Okay, so we have two constants that are not known at this point. We will try to determine them. Okay, so we have this infinite slab assumption. So we have limit x goes to infinity, tau xs being equal to 0, and that would require that k2 is equal to 0. Why? Because if x goes to 0 and k is not 0, that would mean the second term will basically diverge. It's going to go to infinity, so we will have no means of making tau xs equals to 0. Okay, so necessarily k2 is equal to 0. Otherwise, second term will grow unbounded. Okay, so we have tau xs being equal to a constant unknown at this point, e to the power minus x square root of s over a. So that's our solution. Okay, now we will use the boundary condition to determine k1. Okay, use the boundary condition. To find k1. So remember, boundary condition at x is equal to 0. Okay, the remaining boundary condition. So tau 0 t is equal to a function of time. Okay, and therefore tau 0 s is equal to again a function of s is the boundary condition. So k1 is given by that particular function. Okay.
Hocam biz burada function of time yazıyoruz ya gene. T işte 0 t falan yazıyoruz. Ama ilk başta bu assumption'ı yaparken şey dememiş miydik? Hani steady state olduğu için time artık bağlı değil.
Biraz daha yüksek konuşur musunuz? Duyamıyorum sizi.
Şimdi daha iyi geliyor hocam.
Evet, buyurun.
Şey demiştik ya bu ilk başta assumption yaparken artık steady state'te yani time'a bağlı değil gibi yapmıştık. Ama mesela siz burada yazarken tau 0t yazmışsınız.
Ama şunu unutmayın. Biz şunu yaptık. Önce bir steady state bulduk. Tamam. Önce bir steady state bir şey bulduk. Bir condition. Daha sonra şunu söylüyoruz. Bu sistem steady state'e geldi. Hiçbir time dependence kalmadı. Bütün steady state değerleri bulduk. Şimdi şunu bulmaya çalışıyoruz. Bu steady state'in üstüne biz boundary'e bir fonksiyon uygularsak, unutmayın boundary condition hala zamanın bir fonksiyonu. Dolayısıyla steady state'e gelmiş bir sisteme ben boundary'de zamanın bir fonksiyonunu uygularsam, bu sistemin içinde steady state'in üzerine transient olarak ne oluyor? Bunu bulmaya çalışıyorum.
Anladım hocam.
Anlatabiliyor muyum? Yani steady state'i bulduk. Hani transistör devrelerini düşünün. Önce DC analiz yaparsınız değil mi? Yani bir DC analiz yaparsınız. Bütün devre elemanlarındaki DC bias voltajlarını bulursunuz. Onlar sizi devre elemanlarının operating pointlerine götürür. Bunların etrafındaki delta variable'lar için bu sisteme bir üzerine steady state'in üzerine bir input uyguladığınızda ne olduğuna bakarsınız. Bunun için tabii ki devreyi işte S domainde analiz etmeniz gerekir yani. Doğru mu? Steady state'i bulurken bir zamana bağlı bir şey kalmadığını varsayıyorsunuz. Elektronik devrelerde zaten bir DC voltaj üzerinden her şeyin, transient'ların bitip her şeyin steady state'e geldiğini varsayıyorsunuz. Burada da aynı şey. Temperature distribution'ın stable bir hale geldiğini, steady state değerine ulaştığını varsayıyorsunuz. Sonra işte bütün bu assumption'larla, infinite step assumption, ondan sonra steady state'in üzerine elinizdeki tek boundary'e bir tau zero of t fonksiyonunu uygulayacaksınız. Şimdi bunu uyguladığınızda içeride ne olduğunu bulmaya çalışıyoruz. Cevap oldu mu?
Evet hocam, teşekkür ederim.
Başka soru var mı arkadaşlar? Okay. So, I guess that's a good point to have a break. And then after the break, we will basically find the time. Okay. So next, how to go back to time, back to a time function. Okay. So you see that we already have the solution in the Laplace domain, because as a function of s, we have what the temperature, the delta variable temperature is. Okay. Assuming that we already know what we apply at the boundary. That means knowing what we are applying at the boundary means we know tau zero of t, and therefore we know what tau zero of s is. In that case, we know what is tau xs. But we still need the time function, the response function, back from the Laplace domain. Okay, we will see that that's not very easy, and in fact we need to resort to some Laplace transform tables, and we end up with a strange function called the complementary error function, which is in fact related to the inverse Laplace transform of this exponential function. Okay, let's have a 10-minute break, and then we will be back for more. Arkadaşlar görüşürüz 10 dakika sonra.